Alright, so we'll start here with our next one. And so we're going to be doing section 4.3, derivatives and shapes of graphs. And so we're going to be looking at a bunch of derivative tests in order to determine the shape and properties of graphs. So let's do that. So the first one is the increasing decreasing test. So remember that our derivative tells us the rate of change, and so if the rate of change is greater than 0 on an interval, the function's increasing. If our rate of change is less than 0, our function's decreasing. And if it is 0, it's remaining constant. Our first derivative test, so suppose C is a critical number. If the sign changes from positive to negative, then it's a local maximum. If f prime goes from negative to positive, that's a local minimum. If the sign does not change, there's a no local maximum or minimum. We're going to talk about concavity. So if the graph f lies above tangent line, this is what we call concave upward, and if it always is below, we call that concave downward. Let me kind of illustrate that before we move on. So here if we have like this is something that is concave up. So this is concave up. And so here we go. So this is concave up. And notice here if I take these tangent lines, graph is always above it. Here I'll draw something which is concave down. And notice here the tangent line is always below it. So this is concave down. Okay, so we call that concavity. And so if it's so if it looks like this, it's concave up. If it looks like this, it's concave down. So an inflection point. So an inflection point is a point on the graph where if f is continuous, the curve goes from concave up to concave down, or concave down to concave up. This will occur where the double prime is equal to 0 does not exist. And a second derivative test, and so if we have f of c equals 0 and the second derivative is less than 0, that's a max, and if it's greater than 0, it equals a minimum. We'll kind of go over all this. Let me kind of quickly draw what an inflection point would look like. Here, if I have a graph, it's concave down, and then at some point I'll switch over to concave up, and right here is where the switch occurs, right? So we call this the inflection point. You'll see more of them. But I just want to give you a quick hint of what this is. So this is the inflection point. Okay. And so this goes from concave down to concave up. So here it's down and goes to up. Notice here our tangent lines are below, and here it's above. Okay. All right. Get rid of this. So let's look at this. Here we have the following. So here we have let f be this function, so minus negative of x minus 1 times x plus 3 cubed. And then here if I take the derivative, we get minus 4x plus x squared. Plus if I take another derivative, I get minus 12 plus x plus 1 plus x plus 3. And so let's just start working through this. So let's state the domain here. So the domain of this, since this is a polynomial, the domain here is all real numbers. So this is all real numbers, or sometimes it's written as minus infinity to infinity. Find the critical numbers, and so we're going to set this equal to 0. So we're going to take f of x prime, and we're going to set that equal to 0, and solve for x. And so where does this equal to 0? Well, this equals to 0 at 0, where x equals to 0, and x equals to minus 3. And so those are our critical numbers. Alright, so now we're going to create a graph, figure out where is it increasing and decreasing. So we're going to do our intervals for here we're going to do our intervals for between our critical numbers, so from minus infinity to negative 3, from negative 3 to 0, and from 0 to infinity. So here we're going to look at our interval from here to here. It is going to be, so if I put negative 5 in, if I put negative 5, so negative 4 times negative 5 would be positive, And then here I'll have -2, but I square it, so this was positive. So overall, the sign here is positive, and so the behavior here is increasing. Here, if I'm going to choose a number between here and here, I'll just take -1. So -4 times -1 is positive. -1 plus 3 is positive. Squared is still positive, so this is all positive. And so this is also increasing. And then from here, from 0 to infinity, here I can just plug in 1. So I have negative here plus positive here will give me an overall negative, so this is decreasing. And so here it's, so we want to find what values of x, where f of x double x, and or where the second derivative is either 0 or undefined. So let's look here. It's not undefined anywhere, but it is 0 between the following. So f double prime of x is double prime of x is equal to 0, which is equal to minus 12 x plus 1 x plus 3. And since this is already factored, we can easily see where this would be 0. This is at 0, of course, at the following, and that is minus 1 and minus 3. So let's go ahead and do the same thing here for concavity. So I'm going to go from minus infinity to -3, from minus 3 to minus 1, and from 1 to infinity. Alright, so the sign here. So now I have this up here. Let's look at the sign. So let's just pick like -5 again. So if I have -5, so I have negative, or negative, negative, negative. So that all multiplies together to be negative. We don't really care what the sign is, so the -12 is always going to be negative. Here, -5 plus this, that's negative. So negative times negative is positive, and then we're going to have a negative here, so that becomes that. We don't care what the value. We're just picking and saying sign is always that. For here, we'll do -2, and let me kind of show you. Actually, I've kind of hand waved it for a second, so let's just look at. So it'll be 12, and then I have -2 plus 1, and then here I have -2 plus 3. Here, if I look at this really carefully, here I have a negative number, I have a positive number, and I have a negative number, and so overall this will be positive. So that's kind of what I'm doing here in my head. Here I'm going to choose 0. It's the easiest number here, so this is negative, positive, and positive. So this is negative. So this is concave down. This is concave up. And this is concave down. So here for the concavity, it's concave down, concave up, concave down. All right, from here, we can kind of tell where our min and maxes are. So let's just look real quick. So when something goes from increasing to decreasing, we have a local max. Here, if we go from up and down, so this will have an inflection point. And this is also, if I go from down to up, it's an inflection, and from up to down, this is also an inflection point. So the inflection here happens at 3, and also at -1, and here we have a local max at 0. Okay, but we'll be more precise than that in a second, so let's just look at that. So list any local max and inflection points. So we did that already from here. So our inflection points. So our inflection points for both of the, points were f double prime of x equal to 0, and that occurred at x equals -1 and -3. Our local min and max. So where was our local max? Our local max was right here at 0. So let's go look at that real quick. So notice, let's do a little bit. Let's use the other. Let's use the other theory. So here we're going to say a local. So we have a local max where here at f of x prime equal to 0. And so we have a local max. Because notice here that f double prime at 0, well, what is that? Well, f double prime at 0 is negative, is less than 0. And so here, if we have this, we have what we call local max, and that's using our theory that we've seen before. Let me just grab that real quick for you. So here, we also be using this theory. So here we have it at 0, here we have it less, and so that's a local maximum. Okay, so we'll have that local max right there. Notice here that the other point, oops, that's at 0. Notice at our other point where f of negative 3 is equal to 0, where f prime is that, our f double prime of minus 3 is also 0. And so we cannot conclude anything from this, so this is inconclusive, right? This is inconclusive, and so we have to rely back here on the chart. So making these charts is important. Because notice that from negative 3 it goes from increasing to still increasing, so it's not a local maximum because it hasn't changed size. Alright, now we're going to want to find all our intercepts here. So let's find our intercepts. So let's just find the easiest intercept, f of 0. So we're going to plug in f of 0. Well, f of 0 is equal to, let's go back to the original f. Just plug in 0 here. So I have minus 0 minus 1, and then 0 plus 3. Yeah, plus 3 cubed. Well, that's just going to be negative 1 times, or negative times negative 1, so it's 1 times 3 cubed, which is 27. So here I have a vertical intercept at 27. Now where's the horizontal intercept? We set this equal to 0 and then solve, so here we'll have x minus 1, x plus 3 cubed. Where is that equal to 0? Well, that's of course when x is equal to 1 and minus 3. So here we have at 0, 1, and at 0, oops, wrong way. 1 is 0, and then at minus 3 is also 0. So these are our horizontal intercepts. Using limits to determine long and behavior. Notice here from what you've been taught before, you really don't have to use limits. So here we have, notice here that right here this is a power 4. So we have, this is a polynomial power 4, and it's negative, and so we know the end behavior here is going to be down and down. But let's just for fun use limits. So let's just go ahead and just do limits and see if that confirms what we know. So as x goes to minus infinity of minus of x minus 1 of x plus 3 cubed equals y. Well, this goes to negative infinity, this goes to negative infinity, so this all goes to positive infinity plus the negative, so this still goes to negative infinity, as we suspect it would. Let's go to the limit as x goes to infinity. Here we have x minus 1, x plus 3 cubed. And here, notice that this goes to positive infinity, this goes to positive infinity, so that goes to positive infinity, minus, so this goes to minus infinity as well. So notice here we have the same behavior. Now with all this, we can sketch the thing, and so let's sketch this thing as best we can. Alright, so let's just zoom on in so I have a little bit more room to work. So we know we have a 0 here at 1, and at 1, sorry. We have a 0 at minus 3. We're going to make this just a normal scale of 1, 2, like this 5. Oops. Move this up here so I can draw a little bit cleaner. There we go. So we have this point, and since I need to get up to like 27, I'm just going to make every 3 of them 10. So that'll be 20, this will be 30, and I need to be up to 27, so something around here. Alright, so here I have 3 points. Here a point, here a point, and here a point. What else do I know? Well, I know at minus 1 I have an inflection point. And And so I'm going to be, so I'm increasing from here. Oops. Hello. So I'm increasing from here to here and decreasing from here onward, because we know that from our graph. So negative infinity to 0, it's increasing and then decreasing afterwards. I know I have concave down until I'm at 3, and then I go to concave up. So negative 1, and then I go back to concave down. And so let's kind of sketch that in. So here I'm coming in from concave down. So here concave down means it's going to be going down like this. And that goes all the way to infinity. Here at negative 1, I'm going to switch from concave. Here I switch to concave up. But notice at negative 1, I'm going to switch back to concave down. So it goes back in the down direction. And I come pretty starkly down and onward. Okay. And so here's a rough sketch of the graph. Now what does it really look like? Well, let's see if we just graph this in Desmos. Ta-da! Here, graphing it in Desmos, we see that our graph looks very, very much like the graph we did. And so we built something really, really close. All right, let's just do this one more time. And now we're going to do it for this right here. So we're going to just do this all one more time for this. Oops. There we go. All right, so let's just do all this again. So here I have a function. I've already done this first two derivatives just to save time. All right, so the first thing we want to do is find our critical point. So here, so we're going to set g prime of x equal to 0. Well, where is this equal to 0? Well, this is equal to 0 when the top part is 0. So that's when x is equal to 4. When x equals 4, this is 0. We also want to know when x prime of x doesn't exist, does not exist. And where is that true? Well, that's true when the bottom part is 0. And that's when x is equal to 0 and 6. And so let's go ahead and run through everything. So v minus infinity to 0, from 0 to 4, from 4 to 6, and then from 6 to infinity. So here's our intervals. Let's look at our f prime, or in this case, sorry, g prime. G prime. So what do we have here? I choose some negative. And so here, if I punch through, just pick a random number and you just kind of plug it in. And so we will get the following as positive, negative, positive, negative, or positive, negative, negative, negative. And you just pick some sample number and plug it in. And so here we have it as decreasing, increasing, decreasing, decreasing. So where do I have? So here I go from decreasing to increasing. And so I have a local min here at 0. So I have a local min here at 0. From increasing to decreasing, I go to, we have a local max here at 4. And from decreasing to decreasing, so there's no change there. All right, so let's look at our concavity. So we're going to set this, set our second derivative equal to 0. That's 0 nowhere, right? It is 0 nowhere. And we can also find out where it doesn't equal, it does not exist. And so our does not exist, in this case, d and e, is equal to 0 and 6 again, right? 0 and 6. X equals 0 and 6. And so we're going to go ahead and run this through. So we have negative infinity to 0, from 0 to 6, and then from 6 to positive infinity. We're going to look at g double prime. We're going to look at the sign on that. So here it's going to be negative, negative, and positive once we crunch through those numbers. And so our concavity here would be down, and down, and then up. So right here we have an inflection point. All right. And then we can just test. Let's get us a couple points. So let's find our vertical intercept. So when we plug in 0, we're going to get 0. Because I plug in 0 into this, I'll get 0 back. If I plug in 0 into this and solve, I get x cubed plus 6 minus x minus a third. And so if I get solved for this, I'll get 0 and 6. So here I get the point 0, 0 again, and I also get the point 6, 0. So here I have a couple points. Let's go ahead and graph them, and here I'm just going to use normal scale. So here we'll have 0, and then we'll go out 1, 2, 3, 4, 5, 6. We'll go ahead and mark our scale here at 5. And so let's just graph it according to what we have here. So what do we know? The concavity. So we have a local min, we have a local max. So we're concave down all the way up until 6, and then here we have a local min, a local max at 4. So let's look at this. So we'll have something come in, concave down here. We have a local min, but now it's increasing. So we've gone from decreasing to increasing, so we need to do that. Still the same. So it comes out, maxes out. Here we have our local max right here, so it goes from increasing to decreasing, comes back down, and then we switch concavity again, and it comes in through. Alright, so what does that look compared to the real one? Well, here we go. Doop, doop. And notice that looks a lot like what we graphed right here, especially if I zoom in a bit. Okay? And so that's what we got here. And that's the end of this section.